We're very happy to have Spencer Chang back from the wilds of Oregon. Um, and he's going to tell us about general amplitudes for beyond the standard model physics.
All right. Well, it's wonderful to be back. I was not, I think the last time I was back, I was not in this building, so it's cool to see the new environment. And as John said, it's like one of your kids coming back, I guess. Anyways, I wanted to tell you about a line of work that was started with Marcus, Dalio, and Miranda a few years back during the pandemic, and continuing it with a couple of my students, Christian, who's still at Oregon, who's my most senior student, Lane, who graduated, Tom, who's a new student, and Gabrielle, who are both young students. And then there's also an ongoing project with Marcus, Tengma, Andre Wolzer, and Francesco. Okay, so I'll just give you some motivation for this general line of thinking about general amplitudes for beyond the standard model physics. And so what I'll try to argue for is why the language of amplitudes is a good way to kind of open up general searches for new physics that's going beyond the standard model. So let me give you just the standard kind of motivation. Is that the things that keeps us up at night is that all our experimental searches are obviously looking for the known new physics, but what if the new physics is some unknown? Are we going to be sensitive to it? And of course, what's most concerning about this is that we've had some very prominent new physics scenarios which have not panned out in these experimental searches. And so it's really kind of made this question, are we looking for new physics in the most general way? And of course, with the ultimate hope to discover something. So in times of crises, usually find a guru who will tell you what you do with your life. And so I guess my guru is Howard Georgia, my advisor. And Howard, especially beyond me, has really been one of the prime promoters of a standard approach in such scenarios where you want to look for new physics in a general way. I summarize as the dogma of effective field theory, that once you've specified what the particle content of your theory and the symmetries, well, then you just write down the most general Lagrangian that respects the symmetries given that particle content, and then you use that Lagrangian as a means to guide your experimental searches. So since we've discovered all the particle content of the standard model, we know at least one approach to looking for new physics is by writing down the general interactions of the standard model and looking for deviations beyond the standard model predictions. And this would be kind of following this sage advice from gurus like Howard or Steve Weinberg, depending on who is your EFT guru.
Since he's your guru, do you know what he thinks of all this activity in SMEF?
I actually don't know. I'm not sure.
I'd really be curious.
I would be curious too.
Yeah.
Something that I should reach out to him. I should certainly share this slide. He'll probably get a kick out of it.
Yeah. You're in much better shape than he is.
He has all the exact living on angels. Okay. Now, I think this is, a very convincing, idea until you try to put it into practice. And so I'll talk a little bit about the reality beyond the kind of theory of using effective field theories, is that they're complicated, that they have other issues. So one of the things that people will kind of really fight is that you are doing things agnostically. You're really looking for things model independently. And when you use an effective field theory, and that's just patently not true, you have to make some assumptions, and those assumptions affect the predictions of your effective field theory. So one common thing you might have heard is there's two proposals for the effective field theory of the standard model, the SMEF or HEF, so either standard model effective field theory or the Higgs effective field theory. And that's about an assumption whether the electroweak symmetry is linear or non-linearly realized in your theory. So that's one assumption, and that can make a difference in the types of correlations in different observables, or with the other part that I'm leading to, is there has to be what's typically called a power counting assumption, which tells you what's the most important leading effects, what are then the sub-leading effects, and so forth. So as to organize all the kind of infinite set of new terms you can write down, you have to make an assumption. And of course, if you make these assumptions, you're not really looking for things modeled independently. You're looking for things that satisfy these assumptions. And so the worry, of course, is that as you make these assumptions, you're going to miss new physics. Okay. The other kind of issue is that they're very complicated, especially if you just kind of think of the standard model effective field theory. Effective field theories for the standard model, they just become very kind of, they kind of explode with complications. So for instance, if you look at the SMEFT effective field theory, the dimension 6 Lagrangian, this one you're parameterizing the most general interactions, has 84 different operators. And so that's already an explosion of new possible interactions. And part of the main problem with this is it's really kind of opaque which ones are dealing with what, because sometimes there may be correlations. This one actually is maybe most dominantly constrained by this, but it might predict something else.
Is that with or without flavor?
I think that's what the flavor is. The assumption
with flavor?
There's no new through the flavor.
Some kind of flavor conservation.
Yeah. And so this explosion really leads to something where the direct connection between the observables that are related to the interactions and these actual parameters of your effective field theory become obscure. And another thing is this basis of how you parameterize the most general Lagrangian has redundancies, and that kind of leads to a couple of non-trivial issues. One, that you have to pin down the operator basis. So some people will say, oh, I like this basis. Some people will choose another basis. So there might have to be a dictionary that relates the different terms. But also just further obscures this connection between operators and observables when the operators might be changing. So I'll talk about some of these things in a little more detail in specific cases, but the idea is that the EFT is potentially the right approach, but it doesn't make our life easy in searching for new physics. And so one approach is to kind of think of a language that kind of connects effective field theories or models to the observables in a more direct way. And so I'm going to try to argue that on-shell scattering amplitudes are that language, that they parameterize the most general interactions, and they avoid some of the issues of interpretability and how closely related they are to observables, right? Because these are the things that, especially at a collider experiment, you would be directly looking for. The primary results that we've obtained is to look at the standard model content and parameterize figure out the number of independent types of scattering amplitudes between standard model particles. So thinking about just from the amplitude point of view, a way to think of this mapping out the most general interactions. We've done this for 3 and 4 point interactions. It could be generalized to higher point interactions, but we haven't seen that an application that needs that, but there may be situations like that. And then I'll show you specific applications that we've done or are in the process of doing using these results. So one is about general lepton flavor violating decays. That's already, I've already pre-printed out on that. And then something in progress with Marcus and others is this concept of thinking about higher order theory uncertainties when you're doing a search for new physics interactions. So that's the idea, the outline of the things I'll talk about, and I'll kind of give you, there's a lot of material, so I'll give you some detail, but please ask questions if anything's unclear. Okay, so let me talk a little bit about on-shell scattering amplitudes. some of the physics of it and how it connects back to the story of EFTs. So let me give you just a specific example. Imagine we're thinking about looking at new physics in the Higgs sector. Well, if you were in SMEF, you would have linear Higgs realization, linear electroweak symmetry realization. So you have a Higgs doublet that part of it gets a vacuum expectation value. So you write down the kinetic term for the Higgs, you write down the mass parameter and the quartic coupling, and everything else above, involving the Higgs would be new physics. And so here I'm just thinking about Higgs only interactions. Okay, so this is the EFT thing where you just go and think of the symmetries is SG2 cross U1, there's Lorentz symmetry, and you just go off and you parameterize this. So under those constraints, you would start with some terms like, H to 6 would just be the natural next step after the quartic coupling. There would be things where you multiply the kinetic term by H squared. This is the dimension 6 kind of Higgs self-interactions. And that's not the only things you need to think about how Higgs interacts and produces signals. So you think about how it's being produced and all that. So if you go to one of these, here I've picked out an Atlas result where they were trying to combine all the Higgs different searches and the constraints on the standard model effective field theory operators. There's, I think, exactly 50 dimension 6 operators here that are involved here. And I'm sorry you can't read this, but I promise you if I blew it up even bigger, you wouldn't necessarily know what everything is involved in. So it wouldn't make it much clearer. The idea is that, yes, this is a way to parameterize our new physics, but it's very, it has all these, these problems that I was mentioning. It's not interpretable, and it seems a little bit removed from the.
So can I ask this
question?
Yeah,
no.
So then how did they choose them? If they don't make any logical sense.
Oh, how did it? Right. So this obviously requires a lot of back and forth between the theorists and the experiments. And so the amplitudes, I would say as well. Of course, if you already know you're looking for a certain type of interaction, you could go and look for what are the parameterized interactions of those types, and that I think is a much clearer approach.
But can I just editorialize?
Oh, sure.
So there's some discussion about. There's one question which is how do they choose which parameters appear in that list? Okay, and that's a relatively rational discussion, and something converged on that. But now you can ask, okay, now how are you going to search for those 50 parameters? Okay, now you know very well because you're an experimentalist that you would need to know some kind of a theoretical prior on those things, like some kind of range, existence of correlations. But they're trying to do this search without any such information. So the search, whatever they're doing, is garbage. Because there's no clear statement, of, you can probably read the details of the paper to see exactly what they do. They do something, but there is no physical input that says what is the range of parameters, and this is also an approximation. How big are the corrections to this? There's no explicit assumption of that.
Can you use their results to learn something about this list then, and groupings thereof, or?
That's what they want to do. But my personal opinion is it's complete garbage.
Okay.
I'm editorializing because they're not making explicit the assumptions.
But that's why he chose Atlas.
The CMS is doing everything.
Right. It's much better at CMS.
Okay, so let me just reiterate the points. There's going to be these operator redundancies, which I'll talk about a little bit more, which is the basis. But I think I've tried to illustrate in a very specific case that there's a lot of parameterization, but the map between what you're actually pinning down when you're doing a search and those operators and their coefficients is very non-intuitive. And there are important assumptions being made in here about what are the most important terms, whether there are correlations between different signals. And so that's part of the reason why we should think about other ways to connect and maybe make this a little more streamlined.
I think you said it better. It's not that they're not making, of course they're making assumptions because they're doing analysis. It's just not obvious what those assumptions are.
Yeah.
Those assumptions are entirely encoded in the way they do the analysis, so it's hard to know how to interpret the results.
And if you were to ask them how they made those cuts or that decision, they probably had some actual model in mind. And
No.
no,
That's the
that
problem.
that was not related to this, and then they are trying to apply it.
No, they really want to say that they're being agnostic.
Oh, I see.
Yeah.
That's what they're trying to do.
But yeah, it's impossible to not
It's
make
impossible
assumptions. Right.
to do that.
Okay. So let me give you an example of this approach. So of using amplitudes. So imagine you were an experimentalist who was looking at vector boson fusion production of two Higgs. Right? So you'd be interested in interactions like these, where you have two W's coming in and two Higgses coming in. So since this is something that the experimentalist will directly be sensitive to in such an analysis, if you can map out all the possible types of interactions that could be here, then that'd be one way to connect directly to the non-standard physics that we may be sensitive to. Okay, so here, what we'll see in the amplitudes is that this is one way to parameterize the general anomalies in any signal, right? By thinking about the interactions you'd be sensitive to, and then let's characterize all those interactions. There's going to be less assumptions because we'll know all the possible structures here. And you could say, well, we could look over all of them, or so since the direct map between the observable and the things are exactly one-to-one, you can think about this kind of what assumptions you're making here more transparently. What you'll see is that part of the reason there were the operator redundancies is that they leave these on-shell scattering amplitudes invariant. And so the redundancies of operators is precisely because they actually predict the same set of amplitudes, but you can choose to parameterize them differently with the operator. And so even though I might be choosing a basis, the basis terms are the same, right? Whereas the operators, you can exchange an operator that doesn't exist in your list with another operator because they might still give you the same scattering amplitudes at the end of the day. So this is a more physical basis in that sense. And then, yeah, we could, hopefully this will be a means in which to let experimentalists look for new physics in a more general way. And that's our hope, but we're going to leave to some of these applications at the end.
Can I just
Yeah.
point out that we don't actually measure amplitudes, we measure cross-section.
That's true, yes. So it's not quite, yeah, so maybe it's direct, but not exact. That's a very good point. That's a very good point. Okay.
Question here about the general philosophy.
Yeah, yes, absolutely.
So, I can see the advantage of this for a single amplitude.
Mm-hmm.
But if I have a Lagrangian, I can look at whatever parameters are in there, and I can then use that to determine any amplitude.
That's right.
Here, if you're doing it amplitude by amplitude,
Mm-hmm.
does that mean just that you need some extra step of comparing each amplitude to each possible other one, or?
Yeah, what I would say is that because you could take this result in a couple of ways. You could say amplitudes are a convenient intermediate step between experiments and the theory of the Lagrangian, right? Because the Lagrangian will predict some amplitude. So we're just kind of cutting or like introducing a middle ground in which maybe people will be able to use as a kind of common language. Or you could say that alone, the amplitudes itself, is defining the theory, so you don't necessarily have to go back to the Lagrangian at the end of the day. That's probably more ambitious, and probably more people would say why we shouldn't make that drastic of a step.
I mean, can't I define amplitudes in such a way that they can't all consistently come from a single Lagrangian?
If you've made some assumptions about what the Lagrangian can have. But I think in the example where you have nonlinear realization of electric symmetry breaking this Higgs effective field theory, and you don't have a power counting assumption there, then I think you can get whatever amplitudes you want.
Well, you can say it like this. This is parameterizing the most general Lagrangian, and it's a one-to-one for the most general Lagrangian. If you have a theory, that's great, right? Then your theory would predict correlations among all of these things. And so you would still want to measure each of these amplitudes, but then you would want to then, as a second step, fit it to the predictions of your Lagrangian that relates the different
It's
ones.
just not obvious to me that for arbitrary collection of amplitudes, that there's going to be any single consistent Lagrangian.
But that is true. This may not be obvious, but it is true. There's
Okay.
a one-to-one map between these amplitudes and the Lagrangian.
Okay, good.
Yeah.
So one thing that's nice about the amplitudes is they give you an understanding of why there are these redundancies in the operators, right? So from the point of view of effective field theory, there are two types of redundancies that we talk about. You can add something to Lagrangian that's a total derivative, and you can just basically set it to 0, and you won't change. You can use that as your Lagrangian. The other thing is you can do field redefinitions where you change the definition of your fields in your Lagrangian. And what that does is it adds terms proportional to the equations of motion of that field. So here's an example where I'm shifting a massive vector boson. You get a shift by its equation of motion. And so anything that is proportional to this, you could remove by a field redefinition. And so effectively, you can also set things that are proportional to equations of motion to 0. So these two effects on the amplitudes are very interpretable. If you use one of these interactions as a total derivative, right, imagine you have a total derivative acting on all the states of in this operator. There's two scalars and two fermions. Then you would get a sum of the incoming momentum from the derivatives minus the sum of the outgoing momentum. And once you impose energy momentum conservation, that vanishes. So that's just energy momentum conservation. So this physical, the manifestation on the amplitudes is if you impose energy momentum conservation, then total derivative interactions do not matter. Here is in the case of the field redefinitions. If you impose the energy the equations of motion, so that this massive vector is on its mass shell, and its polarizations are physical, so that epsilon dot p is equal to 0, then you will get an interaction that's proportional to the equation of motions will vanish. And so, for instance, if we were picking this one, this vector had a new interaction that was just proportional to this equation of motion, it would not contribute an on-shell amplitude. And so that's how you understand it. So since there's this one-to-one map between redundancies, right, it's not surprising that when you look at the on-shell amplitudes and count them, you count the same number of independent operators. But here, these are the invariants, right? The total types of amplitudes, the amplitudes you can write down are the things that are not changing. Whereas the operators, you can choose to move from different sets. So the basis, even the basis terms are not unique over here, whereas the basis terms are unique. So that's one of the many reasons why we think operators are pretty poor language to connect to experiment. We should really be thinking about amplitudes as being part of the discussion. Okay, and so here let me walk you through an analysis that we did, Marcus, Miranda, and Da did a few years ago. So here let me use that specific example, 2 W's going to 2 Higgses. And let's just try to write down all the possible amplitudes here that we could write down. So here we have, for each particle, we have its momentum and polarizations if there are. The W's are the only things that have polarization here. And here, what we're going to assume is that we have SU3 cross U1 gauge invariance, so we're not assuming linearly realized electricity. And so there are 4 constraints that this amplitude has to satisfy. First of all, energy momentum conservation. So P1. So let's assume that it's WW goes to 2 Higgses. So here there's just simple, the energy and momentum coming in has to be the ones going out. So we can remove one of these degrees of freedom. We could say remove P4 and write the amplitude in terms of P1, P2, and P3, and we'd be parameterizing all the possible momentum that way. We need to impose that the polarizations are physical. So, the epsilon of a particle and its momentum, when you dot product them, vanish. The amplitude itself depends linearly on the polarizations, and is also a Lorentz invariant. So to build things out of this, we need to use Lorentz invariant dot products, or we can use the epsilon tensor in some cases. And then finally, because the Higgs particles are indistinguishable, we want the amplitude to be unchanged when you exchange all the properties of the two Higgses. In this case, it's just P3 goes to P4 because there's no other degrees of freedom. So let's write down some of the terms we could write down. So here, some of the Lorentz invariant products we can just write down. There's S, T, and U for the Mandelstam variables. Now, only 2 of those are actually independent, right? Under once you impose energy momentum conservation, and it works nicely to think of S and T minus U squared because these are the ones that are invariant when you go from H to H, right? When you take P3 to P4. Here, this you could write as P3 plus P4 squared. Right, so that's obviously unchanged if you take P3 to P4. Here, T and U, you can see it in this form where it's P1 minus P3 squared for T, P1 minus P4 squared for U, that when you exchange P3 and P4, the thing before you square it goes to minus itself. If you square it, then it's invariant. It's roughly the angle between the two, the scattering angle squared. Okay, so let's write down some of the terms. So we kind of work by increasing mass dimension, thinking of the type of operator that would generate that amplitude. So here, since it has to be linearly proportional to epsilon 1 and epsilon 2, the first Lorentz invariant we could do is just epsilon 1 dot epsilon 2. Then we move on to things that can involve momenta. Then you can't do epsilon 1 dot P1 because that'll vanish, but you could do epsilon 1 dot P2 and epsilon 2 dot P1. This is also invariant when you take P3 to P4 because there's no P3 and P4 involved, right? Here you could put a term that has epsilon 1 dot to P3 plus P4 and then epsilon 2 dot P1. This will be invariant under P3 and P4 being switched because it's just the sum of the two. If you had the minus, it would be odd, and that wouldn't be good. Here's another term where I just do the same thing for epsilon 2 dot to P3 plus P4. You could have also done epsilon 1 dot P3 plus P4 and epsilon 2 dot P3 plus P4, but we'll show that's actually unchanged. And then here's if you go to, actually this is another possibility, epsilon 1 dot to P3. So both of these are dotted to P3, and then you switch the term where P3 and P4 each. Okay? So these are, it looks like we've had at least 5 terms that might have been non-trivial. But you can show that C3, C4, and C2 actually are all the same because using energy momentum conservation, this is P1 plus P2, but P1 dot epsilon 1 vanishes, so it's just P2 dot epsilon 1. So it's exactly this term. A similar analysis happens for C4, so actually they're all the same term. C5 is a different term, so far as we can tell right now. So these are terms that are invariant under the P3 to P4 exchange. And of course, we could always multiply by any factors of S or T minus U squared because it would still be invariant under P3 and P4 exchange. And so that's one set of new amplitude to write down. But you could also go potentially higher with more momentas. Okay. Yeah.
So why does epsilon 1 dot P1 vanish?
It's just because it's a physical polarization, right? So they're supposed to be orthogonal to each other.
The
Right?
longitudinal W.
Yes. So the longitudinal W has the transverse and the longitudinal polarization.
Right.
And so you need to get rid of the one that would be exactly along key. Well, it's not exactly along key, but it's the one that, you can have the transverse and longitudinal, but that's not a fourth polarization. So that's the one that gets rid of it. Yeah, for instance, in the rest frame where the energy momentum is just along the time component, the energy, then the only polarization that disappears is that it's not physical, it's the time-like one, right? Because it could be polarized around X, Y, and Z. Okay, so in this example, we see that, even though we had 5 coefficients before, they actually become 3, this A1, A2, and A3, where it's just rewritten in terms of these other coefficients that I had before as C. And so we see that those 5 terms are actually secretly 3 terms, right? So even though we were able to write down 5 terms, we see only 3 independent ones. So this is a very simple example, but when we start looking at more complicated examples, we actually have hundreds of terms. We want to automate this so that we don't, have to painstakingly figure out, what's the relationships between these. So in this case, what you can do is take these amplitude pieces and take derivatives with respect to the underlying coefficients and form a matrix that's not necessarily square, but you can do the singular value decomposition of this. In this case, you see that there's 3 non-zero singular values, so there's 3 non-zero independent terms. And so this is kind of a very simple example of the thing that we were doing to figure out a numerical way to find the number of independents. Okay, so at the end of the day, for this example, we can write down a general polynomial in variables of s, t minus u squared, times some kind of primary, kind of fundamental amplitudes that we call primary amplitudes. And so these amplitudes dressed by these Mandelstam factors give you the full set of amplitudes, and we have this distinction of primary amplitudes where there's no dependence on the Mandelstams, and then descendants where you multiply them. Okay, so this is just a table of the interaction, or the amplitudes that we've been able to determine of the primary amplitudes. We write in terms of operators, but since these operators are just the 4 fields, you can immediately tell what the amplitude is. And so here we see a primary amplitude that's related to a dimension 4 operator, then 3 that are dimension 6, and then 5 that are dimension 8. We've also listed the CP properties here as well. And so, so what our result is saying is that there's 1 primary in dimension 4, 3 in dimension 6, 5 in dimension 8. And so you might not trust our numerical result. So is there any way to cross-check this? We are able to cross-check it with an approach called the Hilbert series, which was developed by these authors to count the number of independent operators. So this is just a calculation in which you can determine how many operators are in each dimension, but it doesn't tell you what the operators are. So it's just it involves a contour integration. And the Hilbert series for this interaction in particular has this form. So there's a variable q, and you get this fraction that comes out. What is q doing is it's really going to be a parameter that allows us to count the operator dimension. Okay, and so think about q as being a small number, smaller than 1, so I can Taylor expand the denominator. Then you get a set of coefficients times powers of q, right? So if you look at the kind of expanded term, the coefficient of the power of q that's to the power d is the number of independent operators at that dimension. Okay? So that's how you interpret this Hilbert series. Q is just a parameter to kind of keep track of the dimension. You look for the coefficients in front, and that'll tell you what the number of operators. So now we can understand this structure as resulting from the primary and descendant structure. So here, for instance, we have this numerator. The numerator is really counting the primary. So if I just ignore the denominator for now, I have q to the 4th, with a coefficient of 1. And so that's that 1 dimension 4 primary that we had on the previous slide. Then there's 3 at dimension 6 and 5 at dimension 8, right? And so those were the exact numbers we had of the number of primaries here. 1 at dimension 4, 3 at dimension 6, 5 at dimension 8. So what are the denominators giving you is when you expand them, for instance, take 1 minus q squared. When you expand that, Taylor expand that around 0, you get 1 plus q squared plus q to the 4th, all powers of even powers of q with coefficient 1, right? And so if you want a power of s, then you have to take, the dimension 2, and that gives you 1 new term, right? If you want 2 factors of s, then you get the q to the 4th because that's dimension 4, and that'll give you 1 new term, right? So forth. The 1 minus q to the 4th is an expansion that's giving you powers of not even powers of q, but powers of q to the 4th plus q to the 8th. And that's counting the t minus u squared things, because that's dimension 4, right? Because it's the square of a Mandel-Stem. And so you can interpret these Hilbert series as the numerator as primary counting, and the denominators as giving you the Mandel-Stems that respect whatever exchange symmetries you have. Here, because there's the exchange symmetry between the h's, you can have s and t minus u squared. But if there was no exchange symmetry, you could have s and t or s and u, whichever you choose. But it'd be 1 minus q squared in the bottom instead.
And is it obvious that the CDs are all integer?
It will be if this is the case, right? Because and they actually all have to be positive, because it has to be a positive number. Mm-hmm. Here it's obvious because you're taking a polynomial with integer coefficients, and then when you Taylor expanding, you're also multiplying by a polynomial with integers, so that will be true. It's not obvious, and so usually if you've made some mistake when calculating this, you'll find it through weird things like this.
Coefficients are 1. Got it.
Yeah. There are some examples which, if I have extra time, I could talk about or offline, where you have negative numbers up here. And that's one of the reasons why this is a cross-check, but it may not be, it's only a cross-check, it's not necessarily telling you exactly the number of primaries. So this is a nice technology that we can borrow and use to check these things, right? So here, everything is panning out, or compared to this table, it looks correct, right? Like we have the primaries, the number of primaries are working out, and we can, so essentially what we're doing when we check this is we have, we work the amplitude up in dimension. We start here, this is the only one in dimension 4. Then we can think of this being dressed by factors of this at dimension 6. So we only have a factor of s, right? So we have, when we go to dimension 6, we have this amplitude plus a linear term that's multiplied by s, and all the possible new primaries there. So these turn out to be the ones that are independent. There's a whole set of other things that could have been independent, and we're just picking out the ones that form the ones that are new independents. And then at dimension 8, you would include all the Mandel-Stems from dimension 4 to get to dimension 8. So now you can do a t minus u squared, you can have an s squared, right, to get to dimension 8. You have these dressed by s, and then you have whatever new possible primaries there, and you check. So what we've done in all the examples is we've always checked, I think, to the one past the non-zero value, so that because there can actually be some cancellations, and at the end I could show you some examples where that's the case. But so we can't say that we know that this is true, like we know all the amplitudes that we've just written down are parameterizing the full thing, because we haven't checked this to infinite dimension, but we've checked it to a pretty high dimension. So with my students, I went and did all these other coefficients. It was very interesting how, like, every time you do something new, it would be new challenges to understand. So basically, here with it looks like we did less and less every time, but so I promise you that's not the case. So with Marcus and company, UC Davis company, right, we did all these ones that involved the Higgs boson, and then we did with Lane, one of my students. We did fermion interactions, so the things that we characterize as postulating for the top quark. And then finally gauge bosons. But of course, we're hiding a lot of structure, right? These are all the possible gauge bosons in the standard model. And so for instance, the 4-gluon one is actually a pretty interesting one in terms of the group theory. So we had a lot of fun working through the mathematics of this. And it led to these three things. Okay. So let me give you an overview of everything so far. So we really think this is a kind of a nice way to go about connecting between experimental, analyses and new physics search, the new physics searches, because this is really kind of avoiding some of the challenges of the EFT approach. We can really think about what exactly are you sensitive to in your experiment, not worry about correlations or assumptions you have to make in the EFT, and of course you can always port those back if you have to go to a theory analysis. So specifically what we've, we've developed a numerical technique, right? We talked about getting the number of independents. And what I think I was especially proud about, and maybe Marcus is too, is that we have this, powerful other check of the Hilbert series, and so we really were confident of our results, and confident enough that when we found mistakes in other approach called using spinor helicity analyses, we were confident enough to say, like, we've really fully explored this and pointed this out to them and said, oh, did you have some errors in your result? And they did. And so even though we felt like we were doing the dumb, caveman technology instead of using spinor helicities, it was actually, it's very powerful. And we go far beyond in mass dimension what other people have done. So the spinor helicity people have mostly worked to dimension 8 and lower, and we've done things to dimension 14, which is, I think dimension 14 is probably the highest we've ever done.
For some of them, we'd go to infinite dimension. Right?
Well, we don't know for sure, right? Because we haven't checked the number of independents each time. We have pretty.
I thought for some of the ones with no symmetry.
Oh, sorry. Yeah, for things like things like scalars, sure.
Yeah, for some things,
but
it's infinite, and then yeah.
That's true. Yeah. Sorry. And so we've completed the analysis for 3 and 4 point interactions of the standard model. And we hope this will really kind of open the door for experimentalists to look for new physics in the most general way. There's this caveat of cancellations in the Hilbert series numerator, which is the only caveat that says that we don't know things to infinite dimension. So I wanted to leave you with some of the kind of the early stuff we're doing to apply this and see where this might lead us, what type of useful new things we can do with it. So I'll give you just 2 examples. This is one with my newest student, Thomas Driscoll, and we're looking at lepton flavor violating decays. So the motivation is that experiments like mu3e and Bell2 will improve muon tau decay to 3 lepton final states by 2 to 3 orders of magnitude. And so these are not lepton flavor violating decays. So like muon to 3, tau to e also, or tau to mu e. Not the ones that are allowed in the standard model, the ones with neutrinos. So those will improve by 2 to 3 orders of magnitude. So it's a possibility that we should be thinking about what ways they might be able to look for new physics beyond, are they looking for the most general interactions? So let's map out those amplitudes that they could be sensitive to as an example of this approach. And we have some estimates to say, well, what mass dimension should they even be considering these general amplitudes to? And so I'm not going to give you the details, but I'm happy to talk offline. We applied unitarity and LEP constraints to show that dimension 6 and dimension 7 operators were the ones they should be sensitive to. And dimension 7 has never been looked at, as far as we know. Only dimension 6. So the leading ones have been looked at, and the dimension 7 ones have not been. So we should see, well, what can the observables in these experiments, how would they be sensitive to distinguishing between dimension 6 and dimension 7? So here's an example. If the 3 leptons at the end of the day are distinguishable, Then you have these 10 dimension 6 amplitudes, and then these dimension 7 ones, there's 8 of them. Okay. And here, because it's a little bit less, there's fewer to look at. For mu to 3, there's 6 dimension 6 operators and 2 dimension 7 operators. And so let's look at the Lorentz invariant. Lorentz invariant. So this should be EE bar actually. I screwed up on the keynote. And this is so this should be in a bar also. There should be one positron. A muon can go to by charge 2 electrons in a positron. Okay, and so here this is the invariant mass of the electron-electron pair, the final 2 particles in this list, and the electron-positron invariant mass. There's 2 choices in each event, right? Because you don't know which of the electron is the one you should be talking about. And so here, if you choose the minimum of the 2 Lorentz, the Lorentz invariant masses of a positron and electron, this is what's plotted here. So this is one way to distinguish which Lorentz invariant I'm plotting. Okay, so you see here there are 3 classes of things that cannot be distinguished just from these Lorentz invariants, right? So there's these 4 dimension 6 operators, and we're assuming just one is turned on at any given time. That's the blue. And so the blue here is close to the green, which is the dimension 7 ones. The 2 dimension, this should be number 2, but that's a typo. The 2 dimension 7 amplitudes, and this is the other 2 dimension 6 amplitudes. So you can see that
the relative normalization is
it's just
arbitrary,
uninormalized.
right?
This is uninormalized.
Yeah.
This is just a shape.
Yeah,
Right. So you
there's
can
no
imagine
prediction
that.
Between,
You can imagine that given an overall rate, right, then we normalized out the total rate in this and then looked at these shapes. So there is some amount of distinguishing power between the green and the blue. It's weaker than obviously between the orange and the green and blue. And luckily at mu to 3, there's actually a highly polarized. I think it was maybe 90% polarized. Yeah.
So what's the minimum?
What's the minimum? Oh, so when you have an electron and a positron here, right? There's 2 electrons. You can form an invariant mass between the positron and electron 1 in your sample for the event and electron 2. You take the smaller of those and that's this variable.
Okay.
Yeah.
And the bottom one is just the other one.
This one's unique because there's only 2 electrons, so you can only have only one pair of electrons. So that
E by E.
This should be E bar E. Sorry.
You don't get anything new from M squared E bar E max.
The other one is constrained by, it's just like the S plus T plus U type.
Oh, I see.
Yeah,
Okay,
so
there's a sum rule.
there's a sum rule for that.
Yeah.
Yeah, there's nothing.
Yeah, of course.
Okay, and so mu3e has a highly polarized muon source, and so if you look at the angle between the polarization vector and the outgoing positron, then it breaks most of these degeneracies. So now these 4 that were in here get broken up into 2 families. So this one and this one. So you've broken half, there's only 2 degeneracies left here and there, and the other ones all get completely broken. So you can see that if you can measure this angular information by having this polarized source, you will gain a lot in terms of breaking the degeneracies. So taus, unfortunately, at Bell 2, there's not going to be, as far as we know, a large amount of polarization information about the taus, and so you can do the same thing with the Lorentz invariance, but it will be less powerful than this one. But this goes to show that at least there is a possibility of seeing new physics of a more general type with this dimension 7, and you could possibly distinguish it, especially if you have this angular information. Okay.
Is there a reason why the blue and the green overlay almost exactly on the bottom plot? But not
Yeah, but on this one, but not over here?
quite?
Or
Yeah.
between this and this?
Yes.
It's probably that the structure is similar. I have to look at the amplitudes. So here it's the similarity between these. So here, unfortunately, I didn't list I did the ones for the distinguishable case. But I can look at it. Yeah, it's probably due to some form of the amplitude.
Can I just ask, aren't there more angles that this is, maybe a lot of them are just.
There's one more
triangular
angle.
Cs?
There's one more angle, and it's less powerful. That's
Okay,
what
this is the most.
Yeah, this one most powerful. I think it does break some of the degeneracies, but it's the kind of deviations, the kind of the discriminating power, but it's not as powerful. Okay, so let me tell you a little bit at the end. Let me talk about what Marcus and I and some friends are doing. So this is related to an ongoing discussion about how do we deal with higher order uncertainties, theory uncertainties in effective field theories. So there's a kind of amusing note from the LHC effective field theory working group. This is amusing if you kind of know some of the politics. So this was roughly 2 years ago. It's truncation, validity, uncertainties. And you can see that there's 4 different submissions. And what's interesting is
Camps.
camps. There are 4 camps, but even some of the camps overlap, right? Like some people are on multiple ones, right? I forget which one. I thought there was one that was somebody's on more than one. Maybe it's okay. I'm not sure. I thought that was the case. So they essentially agreed to disagree and put out exactly what their proposals are. And I believe we're going. Oh, maybe I was because I missed E or something. And we might be G.
We're now G, and we've taken Andrea Volzer out of.
That's
Y.
true. Andrea has
We've
seen the
removed him
error
from
of his ways and is coming our way.
Ambush or
No, he's like a convert to our.
Yeah, he's a convert.
He's a convert. So what's the underlying issue? Is if you look at any of these effective field theory operators that people are looking for, they predict that there is the most discrepant area compared to the standard model is going to be at high energy. So anytime you have any way to cut towards events that are probing high energy, you're going to be preferentially looking for, purifying towards the new physics signal. And that's great, right? That's a way to get away from the standard model background and enhance your ability to look for new physics. But the problem is, part of the reason why these are, important at high energies is because you're essentially adding new higher dimensional operators to the standard model. And those are going to grow, giving amplitudes that grow with energy. And so you have to ask, well, what about even higher dimensional operators? What is this going to cause? Is that going to invalidate my search? Or is it going to be even more important, right? So you have to kind of have a scheme to do this. You'll see in some cases, like part of the issue is that, well, in effective field theory, for example, if you assume dimension 6 is the dominant one, you can look for dimension 6 interfering with the standard model. It'll look like a standard model, amplitude interfering with dimension 6. But if interference, can go negative and be destructive and give you negative cross sections after a while, right? And so that's part of the issue, because if you square the dimension 6 operator, it's as big as a dimension 8 operator interfering with the standard model. So that's part of the kind of the weirdness in the ongoing discussion here, is being led by kind of unphysical results and how do you handle them. So we're going to try to throw ourselves into this this kind of political fight, and our philosophy or kind of motivation was largely driven by this kind of structure of amplitudes, right? So thinking about when I have a new physics signal, I'm going to have some primary amplitude, I'll weight it by some coupling, G, EFT. And of course, there are always going to be the descendants, unless there was some kind of weird structure. But in general, there should be the descendants of, multiplying by factors of S and T. If, for instance, there's no kind of symmetry that you have, Mandel-stems of S and T are allowed. And we're parameterizing this way where there's a new physics scale lambda, capital lambda. And so here, all I have left are dimensionless coefficients, CS and CT. And you can keep going if you would like. Right? And so what we're proposing is that we should at least be sensitive to these type of higher order terms. Right? Because there's no real reason why the primaries, the descendants of a given primary don't appear. Okay? And these coefficients, if lambda is the scale of the new physics, like there's a new particle there, we should expect these to be order 1. So we have some theory prior that we're putting in that these can't be too small so that they're, that they're essentially, set to 0. We expect that there aren't large tunings, and so you can't have this much smaller than 1. Okay. And so what we'll do is we'll look at scenarios where we're going to have no new physics, so it's just the same model, and we're going to set a constraint on this coupling, and we'll do this by marginalizing over the values of these higher order uncertainties. So that essentially we're making a conservative limit because we're allowing these to go, up to penalties given by our theory prior. We allow these to kind of cancel if we need to cancel, or whatever values they need to get the weakest constraint on the coupling. Okay, so we're trying to be very conservative in terms of what can happen with the theory uncertainties, these higher order terms, up to the theory priors we're putting on. Okay, so let me give you, a kind of a cartoon of the results that we're obtaining, and we're still trying to work through some other scenarios. But here, this is lambda on the x-axis. On the y-axis, it's the constraint on the effective field theory coupling. And what's being shown is, well, okay, we're varying what this cutoff is. This is assuming there's no new physics, so we're seeing the standard model. And here our approach to the analysis. So here's where we don't include any of the higher order uncertainties. Here we include one more, and we get a weaker constraint, right? So going up allows a larger value of the coupling, and we see that the nuisances as you increase the number of nuisances, it gets weaker. But what's nice is that as you increase the number of nuisances, it doesn't continue to jump up. It's starting to converge, especially as you're kind of at larger EFT cutoffs, where you don't expect the kind of next order uncertainty to be important, right? It starts to become less and less important. Of course, you make the EFT cutoff very low, there is still some slower convergence, but it still starts to converge. Another thing that's being shown is some UV models where you want to see what would be the constraint if we actually had that UV model on the GEFT. And you can see that, well, with 0 nuisances, you would actually say you should get a stronger constraint by the 0 nuisance analysis than actually what's happening in that model. So this is showing you that you could actually have too strong of a constraint even if this was the model that you should be, the UV model that you should be studying. But if you already have one nuisance, you can see that everything's more conservative than the actual constraint in that UV model. So we think it has some of the properties that we would like. It's allowing us to get a more conservative constraint so that it can be, in any model which it applies to, we don't actually over-constrain it. And we see a nice kind of convergence so that it doesn't require too many new parameters to get more or less the right result, or to a converged result. One of the things that we're looking at now is this is good for our constraints, but we also want to see if it works for discovery. Imagine this was actually the data was due to one of these UV models. How does this respond in the case of an anomaly? That's something we're still in progress thinking about. So to summarize here, we see that nuisances give us a more conservative constraint, but and that it doesn't constrain the UV model that we've injected, or kind of that we should be thinking about, because we're not injecting the signal here. We're assuming it's the standard model. And there are other techniques that are pretty popular, like Andre was involved with clipping, which can make mistakes like this. You can actually get a stronger constraint than actually than the model. So it looks a little bit like the blue curve. And so we have this nice convergence after including a few parameters. So it seems like this isn't at least onerous that you have to kind of really marginalize over several. So this is ongoing. I think Marcus is giving a talk next week at one of these EFT working group, what they call meetings. And so hopefully we'll see if people respond positively. But we really think this has some of the nice properties that that any solution to this should work. So, yeah. All right.
Sorry, can I?
Yeah.
I didn't understand the
Yeah.
back and the 15 TV and the 25 TV.
Yeah.
These two horizontal lines.
Yeah, these are two horizontal lines where if you, let's see, if you here, right? So when you inject the standard model, right?
This is you putting some laptop code.
Yeah, so this is a leptoquark
Just
that
to be
can
clear.
generate the same final state.
This is with, the data is assumed to be the standard model.
Right.
But you're doing an optimized search for these different models.
Right.
So there's no signal in the data.
Yeah.
You're searching for a leptoquark at say 15 TeV with an optimized search. So you kind of are getting the best possible bound on that model, right? And then you're comparing with the same data with an EFT search, which of course doesn't describe the data, doesn't, yeah. Right?
Right.
And for the same value of GEFT, right? So in other words, the 15 and the 25 TeV leptoquark give the same
Okay,
value
so-
of GEFT.
So actually ignore they are horizontal because they don't depend on lambda.
Yeah, that's right.
Okay.
Right, so you can say
forget
that
about lambda.
these
So
ones,
these-
right? Yeah, we're just showing that, like here, where you might need to be, right? So here you can see that any value of lambda that's of similar size to the cutoff actually gives a stronger constraint for just 0 nuisances, right? And so you need to include, or actually 1 nuisance, 0 nuisance, sorry. And then so you have 1 nuisances, you're conservative enough that it's consistent with it, right? Even if you're at lambdas, at the right kind of lambdas that you would expect. Right, so here, right, you really are using the new physics signals specific, the UV theory's specific predictions to set a bound on GFT. And so that always should be stronger than this more generic search.
Okay, you say a good message should lie above the
Yes.
calculus.
And should converge to the black line at large values,
Yes.
right? Because if the cutoff is really large, you could of course make a conservative search by just having no constraint, for example, right?
Yeah.
Just have a really crappy method. But it actually converges. The EFT is perfect, it's working well, but it's conservative for smaller values of lambda.
So Marcus will convince everybody that, all right, next week there'll be one proposal, right? Okay.
Everybody will ask, why is it called proposal G?
Proposal G, the only one.
There's only one.
Okay, let me very quick. I'm already all over time, so let me just quickly conclude. We've mapped out these on-shell amplitudes. We've done 3 and 4 point. There's some, I wanted to think about whether there's 5 points that might be interesting in certain cases. But this seems like it's pretty powerful. We're able to study these and have it for people to use for applications. Yeah, and I really think it helps with some of the issues with EFTs. There's nothing necessarily wrong with EFTs, but I think this really kind of highlights, kind of what assumptions are going into EFTs, and do you really want to making those assumptions when you're doing certain experimental analyses? And then I've shown you a few applications. There's many other ideas that we could, of course, explore, but I think these are the ones that we can most on channel. So this one we talk about. So here's your ending slide, always with like whenever you try to promote that there's a more general way to look for new physics, you're always worried you're only looking for methods. So I'll just end with that.
New physics doesn't look like that.
It's just mocking us.
So for effective field theory,
Yes.
the philosophy is that if UV completed, it will be renormalizable, so we don't worry about like it.
It could be. I mean, it could also just be another effective field theory where you have one new particle or a couple of new particles, and then, right? I'm not sure anybody would, even the EFT people would necessarily, like, it really is for people who think they can get a grand unified theory or a string theory, which really thinks that will converge on something that's completely normalizable, right? I think most effective field theorists would think that we're just going to continue to have towers of effective field theory up to, right, as long as we probe.
Okay, and I think right now there's a like new signal in B meson oscillation. Can effective field theory fit something to that?
I mean, a big
That's very complicated.
a big industry like, Wolfgang will write a paper every time there's a B physics anomaly, right? And he'll say like, oh yeah, these operators with these Wilson coefficients seem to work best given all the flavor, observables, and so yeah, there's a whole developed, technology.
And the basic idea is the same, just expand it Lagrangian.
Yeah, exactly. Yeah, they're working to the first dimension 6.
So those experiments, they're sensitive to the operators at much lower energies, so they don't need to worry about these corrections that we're worried about at high energy LHC experiments.
So they do like.
So they can just do the effective operator analysis without any worries at all.
Right.
And so
assuming there's no new light physics. Right?
Yeah, assuming there's new light physics, but it's just, that's the gold standard actually for experimental EFT analyses.
Is it like they don't discuss higher than dimension 4 operator, or what's the scale exactly?
I think I would say, so their effective theory is even below the W and Z mass. And in that effective theory, they're basically looking at dimension 6 operators,
And
or Fermi operators.
and anything beyond dimension 6 shouldn't have effect on that.
You can assume that it's small, and that's true in a huge class of models. So that's a very reasonable assumption.
Back when you were defining what was allowed in the possible amplitude
Yeah.
from WW to HH,
Yeah.
you said that you assumed that the amplitude is linearly dependent
Yes.
on the polarization factor.
Yes.
Why is that?
It's a standard thing where, like, the way that amplitudes go, right? Effectively, what happens? It's like the wave function, essentially, right? It's just saying when you, when you have an initial state, gauge boson, it's going to be epsilon, that polarization dotted into some vector to give you that. So it's assuming that there's just one epsilon, and there has to be one epsilon, but there's no more.
So I wouldn't have epsilon 1 dot P3 and epsilon 1 dot P4.
Yeah, you can't do that. That's right.
Okay, and that's just because of how it factorizes with the Lorentz indices?
Yeah, that's right. Yeah,
Okay.
essentially. We need to do scattering amplitudes with kind of things with polarization.
Okay.
Well, I don't have any questions. Anybody else have any questions?
Well, so what if you have magnetic monopole?
Magnetic monopole.
Yeah, well, I think you should work on the MSM, the monopole standard model, right?
Yeah, you have to fire at the top of
The
the Chang.
monopole.
I wouldn't know how to,
The effective
to
field
treat
theory
that.
of a monopole coupled to the standard model.
There's always
The MSM.
challenges
Complete
thinking
set of operators.
It's more minimal than the SSM. Tell even from the name.
I think what Steve was asking at the
Yeah.
beginning
Yes.
about if you write down a bunch of amplitudes
Yes.
with independent parameters for
Yes.
every amplitude,
Yes.
then there's more parameters than the Lagrangian.
No, but it's the same number.
Well,
As far as we
I mean-
know, right? Like once you've imposed, like in heft, you would just impose something like SU3 cross U1, right? And then you can do the counting. That's why the Hilbert series works, right? Like we're assuming when we write down the Hilbert series, we've made some assumption of what are the symmetries of the EFT, those are also symmetries of the amplitudes. And as far as we've ever seen, there's always a one-to-one counting of the amplitudes that are mapped onto the operators of a certain dimension.
What I was going to say was, I mean, it's not something you have to worry about now. If you write down a bunch of amplitudes and then find that it's not consistent with Lagrangians, you need even bigger discovery. So.
Yeah, I would guess that what would happen in that case, if you found some amplitudes and it's not agreeing with the Lagrangian, well, one of the amplitudes is wrong because there's an anomaly.
That's the most
That's the most
likely.
negative.
No.
But the other thing is maybe our assumption about the EFC was wrong, right?
Yeah.
So that's why it doesn't fit the.
It's not that there's secretly something hiding in here that's not Lagrangian. No, that's not possible,
Yes.
because you can just think of these as the Feynman rules.
Yeah.
Just like if you wrote down an arbitrary set of Feynman rules, that would be an arbitrary Lagrangian. This is no deeper than that.
Yeah.
Except that you have to think a little bit about what happens with field redefinitions and things like that. But it's really just that. This is an arbitrary set of Feynman rules. You can think of it in that way.
Yeah.
So we're never going to, we're not accidentally stepping into the swampland. Well, swampland for sure, we're in the swampland. But, I mean, we're not stepping into non-Lagrangian field theory by accident here.
Unless we made a mistake.
Well, yeah.